Hi, I'm Arthur Wang. This is my Lab 4 Oscillations lab. So the experiment. We will use Tracker to extract the position data of the mass in a provided video. Note that in your analysis, the values of the calibration length, time between video frames, and the physical characteristics of the system. For example, mass, spring stiffness, relaxed length are the same as the vertically oscillating mass discussed in the video lectures. We will then construct an observed position versus time graph through the use of Tracker to analyze the video. We will then copy the position data, only x and y and y position of the mass, to a spreadsheet and save that data. Finally, we will compare the predicted motion and the observed motion of the mass in both the x and y directions and plot the energy changes that you compute in the model, the change in kinetic energy, the change in gravitational potential energy, the change in spring potential energy, and the change in total energy. Alright, so this is the subject of my experiment. My experiment examines the following provided video. As seen, we will be analyzing the position of the ball at the end of the spring. Relevant formulas and initial conditions. So we have the velocity update and we have position update from Newton's second law. And then we have the mass of the object given through pre-lecture videos. We have this gravitational constant. We have this equation Fg equals mg for gravity. And then we have k equals 4 times pi squared m divided by t, where t is the period of oscillation. And then Fs equals Ks, spring stretch force, and mg equals Ks to solve for the components. Alright, so the tracker data looks like this. You can see as the x goes down, the y also goes up, and they basically go up and down in opposite times. Alright, so applying the formulas to the computational model. So the time interval was chosen based on the tracker data for consistency. The velocity update uses the Newton's second law. V final equals V initial plus F net divided by mass times delta t. Position update uses R final equals R initial plus V average times delta t. The code is here. These are all, a lot of these constants are found in the pre-lecture video. And this is the computation where we are trying to find the different forces that are part of the net force here. So F spring is calculated here, F grav here, and they cancel out or give you F net. And then this is where the velocity is being updated, and this is where the position is being updated. And then we need to also update the springs force and data because it's not a constant force. So these will update over time based on these equations. And then we calculate the energies down here with these formulas. Alright, so this is what GlowScript shows. This is, I guess, how the thing moves over time. Kind of weird to show in GlowScript, but we have this graph here: delta K, delta U grav, delta U spring, delta E, and then we have this part where this one goes up and this one goes down, so they're in opposite directions. One is kinetic and one is potential, which makes sense because for the energy principle to hold up, you need to have kinetic be at its largest when your potential is at its least, so they will cancel out. Alright, so for the tracker and model comparison, we have x and y positions seem to have peaks and troughs at opposite times. They oscillate in opposing directions. So at opposite times, that's where we showed in the tracker data. They went up and down at opposite times. So the tracker data calibration may be a little inaccurate, but the model was developed to emulate the motion based off the same dataset, so any errors are made minimal. So for follow-up questions, what does it mean? For your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. Yes, as the kinetic energy is at its largest, the potential energy is at its smallest, and vice versa. Thus, the energy principle equation E equals K plus UG plus US is fulfilled, because K will cancel out with UG and US. And then using the data you obtained in Tracker. Make two separate estimates of oscillation periods, first by estimating the period of oscillation from the x position data, and second by estimating the period of oscillation from the y position data. Compare the two estimates and discuss. So by analyzing, the graphs, we have 4 seconds for the y direction and 5 seconds for the x direction, though they do seem to fluctuate at opposite times and opposing directions at any particular point in time. Thank you.